as a student, whenever you see a new graph theoretic concept, it is important for you to ask, what can I do with it? Can I make a small Android application with it? Right? So can I convert it into something that changes somebody else's life? That we can't teach here. Right? That you should practice, right? And that can never be taught. Right? So now let's go down to greater detail and identify specific things in graphs, right? And ask for properties of these specific things. Right? So let's look at a graph G. No weights, and for this lecture currently I am going to only talk about undirected graphs, and otherwise graphs that represent symmetric relationships. Right? The simplest property that you can look at in the graph when you see the graph is to ask how many edges are incident on it. And this is the most natural thing. If you go to a city and if you start walking around the city, you sometimes don't know anything about the topology of the area, but you know that you were at this place and there were two roads going out of this place. Right? You had crossed this particular signal when you were in the bus and you saw that there were 4 roads going out of it. Right? So therefore, very easily you can keep track of how many edges are there, right, at a particular vertex in the graph. Right? So now let us see what are the properties of the degrees of every vertex, right? So I am going to define this concept now. So the simplest and most natural is the concept of the degree of a vertex. The degree of the vertex is a positive integer, as you will see quite obviously. Right? For a vertex V, n of V is called the neighbors of V. Right? N of V, the neighbors of V is the set of U such that UV is in E. Right? The degree of V represented by dV is the number of elements in N of V. Fine. Let's try to prove a whole sequence of non-trivial properties, right, based on the nature of the degrees. Right. They are easy properties, but they are non-trivial, meaning that when you go through a road network, you don't think of them. But if you ask a graph theorist, the graph theorist will tell you some nice properties of them. Right. So they are non-trivial, but not easy to prove. Non-trivial to think about or observe, but the proofs are not very easy. Right. So let us look at the most obvious one, which most of you know. What can you say about summation dV? What kind of a mathematical statement? How many of you know the answer to this question? Summation dV, V belonging to V. Okay. I have not asked the question, but already some of you have asked the question and probably answered it because you've seen it. But what I want to show you is that you can ask a whole variety of questions. Right? So what is the most natural question that is associated with this? Yeah, don't worry about the concept. I'm just asking you, if a graph is given to you and if you consider this number, summation dV, what kind of a question can you ask about this number? Pardon? Okay, very good. So one question he asks is there a relationship between the number of edges and this term? That's correct, right? It's probably because you believe you know, you've already seen such thing or you know it before. But I would say the most important or the simplest question that you can ask is what a second or third standard kid would ask, is this number odd or even? Is it odd or even? It is even, right? So the question is non-trivial because you have to think about it. It doesn't come automatically, but once you ask the question, the answer is immediate, right? So therefore, what you will see throughout this study is that people ask very, very interesting questions, and asking the question is a good first step, and there is no classification of whether a question is a good question or a bad question. After asking the question, the answer can be easy or the answer can be hard. This is something that you should keep in mind, and you should not stop yourself from asking any question about that particular concept. So the obvious thing is, if you design summation dVV belonging to V, what is its parity, right? It is even, quite obviously, because every edge gets counted twice. Every edge has two endpoints. That edge will get counted at both the endpoints once. Therefore, this will always be an even number, right? So therefore, it is even. Nothing should now prevent you from writing other kinds of crazy mathematical formulae involving the degree and simply asking whether it is odd or even. Right? Very clever mathematicians all over the world have the ability to do this. Right? I've given you the most simplest mathematical function, just add the degrees. Right? What prevents you from doing something like multiplying the degrees or writing a complicated polynomial expression? So go identify a polynomial, and inside the polynomial you substitute all these degrees and show me properties of that polynomial. What am I telling you? I am telling you that just this single idea, right, opens a minefield of research questions that you can play with, right? So therefore, here the answer is very easy. Indeed, as one of your friends probably pointed out, and their analysis also shows, this is twice the total number of edges. The answer is extremely easy. It is just a very simple counting argument. Right. So you have a graph G. There is an additional property. By the way, n means the number of vertices. Right. Throughout the lectures, I will use m for the number of edges and n for the number of vertices. Right. So what do you have? You have a graph in which the minimum degree is at least n by 2 plus 1. Right. So let me also make it very precise. Right. So to make it an integer valued function, let me say floor of n by 2 plus 1. Right. So example, here is a graph where the degree of every vertex is 2, right, and its degree is at least n by 2 plus 1. Right. So you can take any graph and do this, right? So as you can see here, in this case the degree of every vertex is just floor of n by 2. 5 divided by 2, floor is 2, plus 1 is this. So in this graph, the degree of every vertex is at least floor of n by 2 plus 1. There is one vertex whose degree is strictly more than the floor of n by 2 plus 1, which is that top vertex. Right? So which has 4, but floor of n by 2 plus 1 is equal to 3. Fine. Now the question is, what can you say about this graph? It's only true for graphs where every edge has exactly 2 vertices. That's correct. Yes. No, it's always true. Always true. Okay, that's a good question. I didn't complete the proof, right? So let us look at this summation, right? How can you write this summation? Basically, you're going to count every edge. So this is a good exercise, right? So it's very easy. So summation dV So what am I doing here? I am completely showing you how to work out the mathematics of that particular claim, right? I am not doing a mental calculation. I am setting up all the variables. So therefore, for some of you, this may be looking as if this is what you want to bound. By definition, it is equal to this guy, right? But how does one capture this cardinality? We capture this cardinality by introducing what I call our indicator variables. You must have studied this in your 12th standard. These are variables which take 1 or 0 value, right? So this is over the vertices. This is also over the vertices, the second summation, and I say xuv, right? What is xuv? Xuv will take a 1 value 1 if the edge uv is in the edge set of the graph. It is equal to 0 otherwise. If the pair u comma v forms an edge, then it takes a value 1, otherwise it takes a value 0. Fine. Now this summation, as you can see, an edge u comma v will be counted exactly twice in this summation, right? Once when v is in the outer summation, u is in the inner summation, and the second time when u is in the outer summation and v is in the inner summation. No other term will be counted. Therefore, this is equal to twice the total number of edges. Right? Actually, it is very, very important for everyone to not allow mental mathematics to interfere into your calculations, right? So whenever you make a calculation claim, it's good to actually complete the calculation, right, as formally as possible, so that there must be no gap, right? So there must not be something where there is a jump which is inside your mind. It must all be in the form of carefully chosen mathematical variables and clear arithmetic and logic that we are aware of. So let's get back to my second question. I give you a graph in which every vertex has degree which is at least n by 2 plus 1, floor of n by 2 plus 1. Right? So now my question is, what can you say about this graph? Is it possible that there are two vertices between which there is no path? What would be the argument? So let's write the claim. The claim for all u comma v, right, there is a path from u to v. So let's try to do a proof of this. Okay. So let us start at a particular u. Right. Its neighborhood is at least the floor of n by 2 plus 1. Right. Which means half the vertices are here. Right. So therefore there are at least n by 2 vertices here. Correct? Because how many vertices are here? It is floor of n by 2 plus 1. What is the least value possible for the floor of n by 2? No, not 2. As a function of n. Right? What is the worst that can happen? You can say that this is at least n by 2 minus 1. That's the worst that can happen, right? N by 2 might be very close to the integer boundary, right? So if you draw the set of integers, right? So n by 2 might be a value which is somewhere here, right? And this is, right, the next integer value. But this next integer value is at least as large as this minus 1. Right? So it's at least as large as this integer value, right? Plus a 1. So therefore, how many vertices do we count here? The total number of vertices that we count here, right, is at least n by 2 plus 1. Right? So just looking at an arbitrary vertex and looking at its neighbors, how many neighbors are there? Floor of n by 2 plus 1. The total number of vertices that you would have counted now is at least n by 2 plus 1, including this particular vertex u. Right? So now you look at how many vertices are remaining, right? At most n by 2 minus 1. Because there are only n vertices in the graph, right? So if you take a vertex here, right, it is not possible that all the neighbors are inside this set. Because if you say all the neighbors are inside this set, you are contradicting the premise that the degree of the vertex is at least floor of n by 2 plus 1. Right? N by 2 minus 1 is smaller than this number. Therefore, there must be one edge that goes from here to here. Right? Therefore, there must always be a path between any two. It's a very simple counting argument. Fine. Right? So therefore, if the degree is high, so in a superficial way of speaking, if every degree is high, then the graph is most likely very connected. Right? Right? You can also prove something stronger, which we have actually done. Right? We can ask, how long is the path between any two? Is it possible that the length of the path between any two is more than some, what do you think? What is the length of the shortest path? How many edges are there? Is it 3, 4, 5, 6 or what is it between any two? Two, somebody said. That's correct, right? Quite obviously, because if you look at u, right, this particular u, v could be here, in which case the path length is 1. If v is here, it is going to have a neighbor here, right? It should be adjacent to somebody here, therefore this path length is 2. Therefore, for any pair, the length is at most the distance. You within 2 hops or 2 edges, you will get to the other vertex. Right? So now I will ask you, if the degree is at most n, is at least n by 3, what can you say about the length of the path between any pair? In general, if it is at least n by k, what can you say about the length of the path? Please take this as a small exercise. It's not for me to evaluate whether you are doing it, but these are the kind of questions that you must ask without fail. Right? So therefore, high degree So now let's prove one more very interesting structural property, right, which is very closely connected to this. I want to show you a very interesting connection. Currently, you are believing that high degree means the distance between any pair is very close. So what I am asking you is that if the degree is very low, right, then you kind of intuitively assume that maybe distance is very large. Right? I mean, if the degree is only 2 means what? Right? Then the graph is one big cycle, no? Then there are 2 vertices whose distance is n by 2. So it's very long, very far away, right? But let's assume that the graph is 3 regular, which means that every vertex has degree exactly equal to 3. Examples of such graphs, you should always try and construct simple examples to start with. So this is a graph in which every vertex has degree 3. Fine. Take a cycle, even cycle, and put a matching set of edges which are disjoint. Just increase everybody's degree by 1. Right? What can you say about the pairwise distance in such a graph? No triangles. Okay, so let me just make this even just for the simplicity of the argument, let me say no odd cycles at all. No odd cycles means that there is no cycle of length 3, 5, 7. Cycle means a sequence of edges that form a cyclic pattern, which you may know. Okay. I'm going to show you that the diameter is, any guesses for the distance between any pair? Do you think it is n by 3, or do you think it is n by 4, or n by 2, or what do you think it is? Okay, the answer is log n, right? And I'm going to show you why it is log n. It's a very slow growing function relative to a linear function. Right? It's a very slow growing function. That is, as the number of vertices increase, right, the diameter is going to increase in a slow way. It is not going to increase as n by 2 or n by 3 or n by 10 or something like that. It's going to increase as logarithmic in n. That is, if you look at graphs with this property, and if you want to know what the distance between any pair and write an upper bound on it, the worst distance possible in such graphs is only logarithmic in n. Right? The answer is very easy. It's just a way of visualizing about it. Right? Start at an arbitrary vertex u. This is the reasoning. Right? Write down its 3 neighbors. It has only 3 neighbors. Right? Then what do? You list both these 2 neighbors of this fellow. Right? Right, and so on. Right? If you are able to put this condition on the graph, then observe the most important thing is that there are 3 vertices here, there are 6 vertices here, and there are 12 vertices here. Right? Therefore, the number of vertices one layer after another is doubling. Therefore, in a logarithmic number of layers, you must have got all the vertices. Right? It's a slightly imprecise statement and a proof. Right? So, I will change it a little later, but what I am pointing out is that you can have very low degree and still have very low diameter in the graph. Diameter means the furthest distance between any pair. Right? Whereas here, you've got the feeling that if the degree is high, then the diameter is low. It is a sufficient condition, but it is not a necessary condition. So like this, just using the degree, you can prove a lot of structural properties. So let me ask you one question. I want you to construct a graph on n vertices with as many edges as possible, but it should not have a triangle. What is the maximum that you can achieve? I want you to construct a graph on n vertices, right? And you must put in as many edges as you can, but the graph should not have at the end the graph should not have a triangle. How many edges can you achieve? Correct, n minus 1 is a tree, right? But you can have n square edges in the graph, no? So is it only n minus 1, or can you use your cleverness and increase it beyond n minus 1? Construct a graph with as many edges as possible, but you should not create a triangle. I will show you one graph, but the book by Douglas West proves that this is the best possible. Beyond this, for every graph, you will have a triangle. So here is the graph. Let us assume n is an even number, put n by 2 edges and put all the edges here. I put n square by 4 edges. Remember, the maximum number of edges that is possible in the graph is n into n minus 1 by 2. NC2, right? I put more than 1/2 of NC2, right? That is, I put n square by 4, and you can see that there is no triangle because left, right, left. There is no edge between left and left, right? So therefore, there is obviously no triangle, but the graph has as many edges, n square by 4 edges as possible. To this graph, you add one more edge, you will always create a triangle. Now I want you to tell me later if I am right or wrong, right? If you take any graph with n square by 4 plus 1 edges, there will always be a triangle. Any graph with n square by 4 plus 1 edges will always have a triangle, will surely have a triangle. It's an exercise, I'm out of time, so I'll stop. Right? So when we meet next, we'll continue this line of study. Right? So essentially it's like graph theoretic puzzles, but we'll build a whole theory on top of this. Thank you.